In this lecture, we will talk about the POVM, that stands for positive operator valued measurements. It's a type of generalized measurement, and this contains every type of measurement allowed on a quantum system. So this is the most general measurement we can have, and any measurement can be written in terms of POVM. Mathematically, a POVM is a set of operators EI, where I is from 1 to n, so there are n number of operators, such that EI for every I is positive, semi-definite for every I, and EI sum over I equals identity. So these are the only two conditions this set of operators, the operators in this set needs to satisfy. That every single one of them should be a positive semi-definite operator, and they all add up to identity. So if we take examples of projective measurements, so the projectors Pi we have are psi I in a projective measurement where psi I forms the orthonormal basis. And so from here we can see that Pi are all positive because their eigenvalues are 1 or 0. And when we add Pi, that is sum over I psi I outer product psi I, since I is an orthonormal and complete basis, this has to be identity. So this becomes valid measurement, and this is one example of the POVM. So a POVM is a set of operators which satisfy these two conditions. Now this seems very general at the moment, but we will see how this can be used to perform measurement and how we extract information about the quantum system using these measurements. So here of course we need to talk about the Bond rule of probability, how that generalizes for POVM, and what is the state after the measurement. So the probability Pi of ith outcome is given by the expectation value of EI, and that is trace of rho times EI. Let us, since EI is a positive operator, we can always write it as AI dagger AI for some matrix AI. We can appropriately choose AI. Then these set of AIs become the measurement operator. And the state after collapse goes to rho I, and that is AI rho AI dagger over Pi. This is a normalization. So these are the two rules. This is the generalized Bond rule of probability, and this is the collapse of the state of the quantum system. Now, one thing to understand here is in POVM we are only given EIs, not AIs, and we can find another set BI, which is omega I times AI, where WI dagger equals WI dagger, WI equals identity. We can have a unitary matrix or many unitary matrices WI. Even then, we see that BI dagger BI is same as AI dagger AI, which is EI. So we, for the same set of POVM operators, we can have many measurement operators. So the measurement, the choice of the measurement operator depends on the experiment we are trying to perform, but the outcome, which is in terms of probabilities, they are independent of the measurement operators. As long as we have the same POVM element EI, we are okay, and we will get the probabilities, the correct probabilities. EIs are called effects. Just the name, that EIs are called effects. So POVMs have n effects, and each effect will give you a probability of measurement, and from that measurement outcome you can estimate the states and things like that. Now we will see, we will elaborate over this POVM, but before that we will talk about a nice theorem. It's called Naimark Dilation Theorem. So what is Naimark Dilation Theorem? It says that any POVM can be lifted to projective measurements on an extended Hilbert space. So what this Naimark Dilation Theorem says is that if we are given any POVM, it means we are given a set of observables EI, a set of effects EI, then we can always extend the Hilbert space. We can have a bigger Hilbert space in which this POVM will look like a projective measurement. And since in the axioms of quantum mechanics, only projective measurements are defined and everything else should be derived from the projective measurement. In that way, this theorem becomes a very important theorem. Because here we are saying that ultimately everything is projective, but if we are trying to look at it from a restricted Hilbert space, then it will look like generalized measurements. So how do we prove this thing? So we are given a set of effects EI. So this is our POVM where EIs are positive, semi-definite, and some over I EI is identity. For the sake of simplicity, in this lecture we will assume that EIs are rank 1 effects. So what does that mean? That means EI we can write as UI out of product UI, where UI is unnormalized. So we are assuming that the effects are rank 1. So we can, and they are positive operators. So rank 1 positive operator means one eigenvalue will be non-zero and all the other eigenvalues will be 0. So the corresponding eigenvector will be UI we are choosing for every EI, and other we don't care. And the eigenvalue has been absorbed in the normalization of the vector UI. So that's why UI is unnormalized. So if we are assuming the EIs are rank 1, then the number of the effects n is from 1 to n. So the n there are n number of effects. So n must be greater than or equal to the dimension of the Hilbert space, because otherwise they will not add up to identity. This condition will not be satisfied if we have EIs to be rank 1 and they are less than the dimension of the Hilbert space. And the equality only holds when all of UIs are orthogonal to each other. Only then the equality can hold. Not will hold, but it can hold when all of them are orthogonal to each other. Now we consider a Hilbert space H prime, okay, which is the Hilbert space of the system, which we are calling H. And then we add another Hilbert space H of n minus d. So the dimension of the Hilbert space H was d, and we add another Hilbert space of n minus d dimension. So the dimension of the Hilbert space H prime is n, and the dimension of the Hilbert space H n minus d is n minus d, and the dimension of H is d. So we can see that dimension of H plus dimension of n minus d, H n minus d total is n, so that's the dimension of H prime. So what we are trying to say is, if there was a vector capital psi from the Hilbert space H prime, then this can be written as a vector of psi, small psi, and a small phi, where psi belongs to H and phi belongs to H of n minus d. It means the dimension of psi is d and the dimension of phi is n minus d. This is what we mean by this symbol. This is what happens to the vector, and we will see what happened to the operator also, and this is called direct sum. So what we have done is we have considered a Hilbert space H prime, which is an extended Hilbert space, in which a part of that is the original Hilbert space H, which belongs to the quantum system, and another part is the extra Hilbert space we have considered. Now we define operator vectors wi, which is ui direct sum ci. So what we are saying is wi is defined in a way that which is ui and ci, where ui belongs to h and ci belongs to h of n minus d. Okay. So if we define a matrix W, which is W1, W2, Wn, then this is a n by n matrix. And if we write it further, it will become U1, U2, Un, C1, C2, Cn. What is W dagger? It is U1, U2, Un, C1, C2, Cn. U1, U2, Un, C1, C2, Cn. And which will become, we multiply this row with this column, we get sum over I, ui, and we multiply this with this, sum over I, ui, ci, and we have ci, ui, and ci, ci. For a moment, just consider this element, and this is nothing but sum over I, ei, which we know is identity. The condition that the sum over I, ui is can be seen from the matrix point of view. We have first d rows of the matrix W. Forget about this last n minus d rows. We are only interested in the first d rows. So they are represented by the ui's, and then we multiply them with themselves, and we get identity. It means all the rows are orthogonal to each other, orthogonal and normalized. All the first d rows are orthogonal and normalized, or mutually orthogonal. Let me write here mutually orthogonal and normalized. This is what it means, that when we multiply the first row with first column, then we get 1. When we multiply with first row with the second column, we get 0, and with the third we get 0, fourth we get 0. Second row with second column we get 1, but everything else is 0. That's how we get identity. That this is what it shows, that all the first d rows are mutually orthogonal to each other, and they are normalized. Well, the inner product is coming out to be 1. So we have a matrix W where first d rows are orthogonal, and rest n minus d rows we have not decided what they are. They can be anything. Till now, ci vectors are unknown. So the next d minus n minus d rows are unknown. Now, if we have n dimensional vectors, n of n minus n dimensional vectors, and d of them are orthogonal, then by using Gram-Schmidt orthogonalization process or by something else, we can make the rest of them also orthogonal. So it's always possible to extend a set of d orthogonal vectors, d n-dimensional orthogonal vectors, to n n-dimensional orthogonal vectors. So we can always choose the n minus d rows which are mutually orthogonal and also orthogonal to the rest d rows. So in that way, by choosing C appropriately, we can have W in which all the rows are orthogonal to each other and normalized. And that's the definition or one of the properties of a unitary operator. So if you have a matrix in which all the rows are normalized and orthogonal to each other, then it's a unitary operator. If you have a matrix which has all the columns normalized and orthogonal to each other, then it's a unitary operator, and they can be independently so by default, if all the rows are normalized and orthogonal to each other, then the columns will also come out to be normalized and orthogonal to each other. So in that way, by choosing C's properly, we have defined Wi, which are Ui plus appropriately chosen Ci, such that the matrix W is a unitary matrix. Then the set Wi represents an orthonormal basis because Wi's are the columns of the matrix W and W is a unitary, so all the columns must be orthogonal to each other. So in that way, by extending the Ui vector to a larger Hilbert space H prime and getting n-dimensional vectors, we have converted it into a part of an orthonormal basis. So now if we perform measurement on the extended Hilbert space H prime in the basis omega I, then it's the orthonormal basis. Then it's a projective measurement. Now, if we have a state rho, which is from the set of which is from the Hilbert space H, then the density matrix rho prime in the extended Hilbert space will look like the following. It will be rho, which is d by d, d-dimensional, 0, 0, and a 0, which is n minus d by n minus d. So this 0 is n minus d by n minus d. This is d by n minus d. This is n minus d by d. So the whole matrix is n by n matrix. So we have just taken the row and padded it up with zeros to make it an n by n square matrix. Now probability Pi was trace of Ei times rho traditionally, in the POVM definition, which is for our POVM will be Ui rho Ui because Ei is just a rank 1 projector, the rank 1 POVM. Then this is same as Wi rho prime Wi because Wi is Ui direct sum Ci, rho prime is rho direct sum 0, and we have Ui direct sum Ci. Here the product goes U will multiply with rho with U and C will multiply with 0 with C. So we get Ui rho Ui. So the projective measurement in the basis Wi on an extended state rho prime is same as performing POVM on rho in the restricted Hilbert space. So in that way, we have gotten a mapping from the POVM in H, this is POVM on H, to projective measurement on H prime. And this is the proof of the Naimark dilation theorem. Any generalized measurement can be thought of as a projective measurement in an extended Hilbert space. Now we move on to how we can use POVM to do the state tomography of a quantum system. So again, let us consider we have a POVM EI, I is from 1 to n. So there are n elements, n effects in this POVM. Now, and the outcome of a measurement are the PIs, which is the expectation value of EI, which is trace of EI rho. Since EI is a Hermitian operator, it's a positive operator, so by default it's a Hermitian operator, so it can be written as EI dagger rho. So it's the same. EI rho and EI dagger rho are the same because EI equals EI rho. Now, if we have if we represent rho vector and EI vector, the unfolded representation of the matrix rho and EI, that is, we take the matrix rho, let us say rho is a 2 by 2 matrix with element A, B, C, D, then the vector rho is A, B, C, D. Just be careful with the sequence, it's 1, 2, 3, 4, not the other way. So this becomes the unfolded vector of the matrix rho corresponding to the matrix rho. Similarly, we can have unfolded vector corresponding to EI. Now, in that way, the probability Pi can be written as EI vector and a rho in a product. Now, if we define a matrix xi, which is E1, E2, E3, and so on up to En, then we can write that xi dagger acting on rho gives us a vector of probabilities P1, P2 up to Pn. And let us see this xi matrix is the d square dimensional by n dimensional, d square by n dimensional matrix. Now, probabilities are what we have as the outcome in the experiment, and we want to do this is the only information given to us in an experiment, and from here we want to see what is the density matrix. And that is what we call the state tomography, that from the experimental data we retrieve the information about the density matrix. Now take a simple case where n equals d square and xi is invertible. If that is the case, then we can simply write rho equals xi dagger inverse acting on vector p. So in that way, we get the unfolded vector rho corresponding to the density matrix rho, and from here we can reconstruct the density matrix rho. In case n is more than d square, but still there are at least d square independent vectors ei, at least d square independent vector ei's. In that case, we consider the equation again. It was xi dagger rho equals p. We can multiply it with xi on both sides. Now xi dagger will be n by d square and d square by xi dagger will be d square by n times n by d square matrix, which is d square by d square matrix. Just let us see that in the beginning n was more, so the xi was a rectangular matrix where the one dimension was bigger than the other. Now both the dimensions are same, it's a square matrix, and as we assume that there are at least d square independent ei's in this xi matrix, so xi dagger is invertible. And in that case, we can write rho to be xi dagger inverse xi p. And hence, we can find the unfolded vector rho corresponding to the density matrix rho, and from there we can reconstruct the density matrix rho. And this is single shot measurement, unlike the measurement we did for qubits, like photonic qubits, where we had to perform first sigma x measurement, then sigma y measurement, then sigma z measurement, and from there construct the density matrix back. Here, if we can find appropriate POVM vectors EIs, effect EIs, from there in the single shot measurement we will get enough data to construct the density matrix rho back. In that way, it can be very, very powerful. We'll be considering more examples where the power of POVMs will be revealed over the projective measurements.